Hello, pre-calculus. Look at this fun changing colors. Hey, so we're gonna play a game. Here's the way the game works. You roll a die, and the only way you win is if you roll a 6. All right, so I've got all the outcomes listed there in the first column. Before I launch into the part of the do now you do on your own, we're gonna do a little bit of it together. So for each of the different outcomes, we're gonna answer this question. How many 6s did you get? That's kind of a weird question. I know you only roll the die one time, but if you rolled a 1, how many 6s did you get? Well, 0. You rolled a 1. If you roll a 2, how many 6s did you get? Also 0. I mean, you rolled a 2, right? If you roll a 3, how many 6s is that? Well, it's still not any 6s. If you roll a 4, there's no 6s. You roll a 5, there's no 6s. What if you rolled a 6? Well, then you got 1 6. Okay. So for each of the different outcomes, it involves or correlates to a different number of 6s. The only way you actually get a 6 is by rolling a 6. We're going to calculate mean, variance, and standard deviation for the number of 6s rolled, which means we are done using that outcome column. We're just going to start from the number of 6s. From this column, find the mean, and then proceed to mean, absolute deviation, variance, standard deviation. Hit pause on the video so you got your answers, and I'll rejoin you when you've finished your work. All right, well, so the mean, we get 0.17. The mean absolute deviation, I didn't actually ask you for, so we can skip that. The variance, 0.14. Standard deviation was 0.37. Nice job. Let's take this one step further. So using the mean, the variance, and the standard deviation that we just calculated, like literally a second ago, now let's see what would be the mean and the standard deviation for how many 6s you'd get if instead of 1 die, you rolled 72 dice. You can hit pause on the video so you get your answers for actually all three, the mean, variance, and standard deviation. Pretty cool. All right, well, so for the mean and the variance, we just take the previous mean and the previous variance, you multiply them by the number of repetitions. You multiply by 72. So for the new mean, we get 12.25, the variance, 10.08. And for the standard deviation, the only way we ever calculate the standard deviation is by doing the square root of the variance. Nicely done. Well, here's what we're going to do today. We're looking at the binomial theorem. Also, it's the subtitle, Bernoulli trials, they're related, but how? We'll find out. So at this point, we just finished that do now. There's a fork in the road, so to speak, in front of us. So we've been working with mean, absolute deviation, variance, standard deviation. We've done how to combine the events and how we can combine means, variance, standard deviation. We've done for repeated events, how we can get the mean, the variance, standard deviation for repetitions. And so at this point, there's a fork, and we're going to take the one road right now to learn about the binomial theorem. And then in a little bit, we're going to come back and we're going to learn about this other branch. So it's kind of a departure point. But we'll come back to mean, absolute deviation, variance, standard deviation in a little while. So today, we're going to learn how to calculate the probability for a specific outcome in a Bernoulli trial. Well, what is a Bernoulli trial? That's a good question. So a Bernoulli trial is actually another name for a binary event. And I know that doesn't really help a whole lot, except binary events, probably a little bit easier to understand. So a binary event is something that has 2 outcomes. Usually we call those success and failure, and really it could be anything. It could be heads and tails. Okay, 2 outcomes, success and failure. Bernoulli is a famous mathematician who studied and came up with a lot of the calculations that we're going to learn, and so binary events are also renamed in his honor. It's called the Bernoulli trial. Trial is a specific statistics vocabulary word that means the number of times the same event is repeated. So our example we just had from the do now involved rolling a die, and a die has obviously more than 2 outcomes, but we can categorize them as either outcomes which lead to success, that'd be rolling a 6, outcomes leading to failure, that'd be the 1, 2, 3, 4, and 5. Okay, so for a Bernoulli trial or a binary event, it doesn't have to actually be literally only 2 outcomes, as long as we can categorize the outcomes into those 2 categories of success and failure. Also, you don't have to have equal odds, because there's only the 1 outcome that gives you success. There's 5 outcomes that give you failure, and that is not even. Right, and that is not an important feature for a Bernoulli trial. We can have different probabilities of success and different probability for failure. So in order to calculate the next thing, the probability of a certain number of successes in a Bernoulli trial, we do that using what is called the binomial theorem. Now, you might have learned about the binomial theorem in some other classes. It's got actually a lot of applications, not just in statistics. So if you haven't yet come across the binomial theorem, chances are you probably will come across it again in a future math class, which you can look forward to it. So here is binomial theorem. Right, so the equation is there in the circle. So that's our formula. Here's how we calculate probability. So the key is up there at the top. So we have these three variables. We need to know what they are. N represents the number of trials. And so from the do now, the last part of the do now, we'd have played the dice game. We rolled 72 dice. That would be N, number of trials, how many times you repeat the event. Okay, N shows up twice. Right here, and again over here in the blue section. So there's two different places we're going to use N. Next in that list, K represents the number of successes. And so if we wanted to find out, hey, what is the probability that if I did 72 dice rolls, I would actually get the expected value of 12, right? Well, 12 would be the number of successes in that case, so I'm going to win 12 times. What's the probability of winning 12 times? Okay, that's K. K shows up in three different spots. It shows up here in orange. It shows up right here in green and over here in blue also. Lastly, the letter P, that represents the probability of success on each individual trial. So even though we're talking about 72 dice rolls, one die, okay, the probability of winning on one die roll is 1 out of 6, right? Because one side out of the 6 is the winning side. And so P is going to be 1/6. We can leave it as a fraction. You change it to a decimal if you want. But P shows up in two different spots, here in green and then over here also in blue. Okay, so as long as we know what numbers to put where, we could totally just take this formula, type the numbers into our calculator, plug and chug, bam, out comes the answer, and we go on our way. But I think as far as learning goes, it's more helpful for us if we really understand where these different parts of the equation are going, or what is their job. So that red part is talking about the number of combinations, right? If I'm going to roll 72 dice and get 12 wins, there's a lot of different combinations of how those 12 wins land. Like, what are the different patterns, right? Is it win, win, lose, 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 win, lose, 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 and so on. Or I change the pattern, right? So there's the order that out of those 72 rolls, where do the 12 wins land? Okay, that's part of this calculation, because it doesn't actually matter what the order is. So there's all these different possibilities of how I could get my 12 wins. Okay, so that's the red part. The green part focuses just on success. What's the probability of success? That's the base. And what is the number of times that I got success? That's the exponent. So if I'm going to use the dice example, 1/6 is my probability of winning. And then if I'm going to get 12 successes, I win 12 times, that'd be my exponent. So everything in green is about wins. And on the other hand, everything in blue is about failures. So the base, that 1 minus P, that's basically the probability of losing, right? We can get it by subtracting. 1 represents like 100%. If you subtract 100% minus the probability of winning, whatever's left is your probability of losing. Or we could just say, look, the blue part has to be focused on failure. What's the probability of failing on each roll? And then the exponent for the blue part is going to be the number of times that you fail. So you could get it as it is written here by subtracting from the whole. If I'm doing 72 dice rolls, subtract the number of wins. If I got 12 wins, 72 minus 12, whatever's left, I need to lose 60 times. I'm going to win 12, I'm going to lose 60, right? Well, let's look at an example. Let's just like this. So I've written this one down already, but I'll explain where these numbers are coming from. So here's the question. What's the probability of rolling 72 dice and getting exactly 8 sixes? Okay, so I'm going to win 8 times. Here's my example. So function notation, probability, P of K equals 8. So K just means successes. So I'm just elaborating a little bit in my function notation. Instead of P of 8, I'm just going to specify, hey, I'm talking about successes. What's the probability of K being 8, number of successes? Okay, so the equation in red, 72C8. There's 72 trials. 8 of them are successes. So that is going to tell me how many different combinations exist where out of the 72 dice rolls, I got 8 wins. Okay, in green, 1/6 to the power of 8. Okay, so the green is all about success. 1/6, because when I roll a die, I have a 1/6 chance of landing on a 6 and winning. Woo! The exponent of 8, that's the number of times that I win. So the question says I'm going to find out the probability of getting exactly 8 6s or exactly 8 wins. So that is my exponent, 8. Okay, then in blue, 5/6. That's the probability of losing. Okay, the only way you win is by rolling a 6. All the other sides lose. 5/6 is the probability I'm going to get one of those other numbers. Okay, and then in blue, the exponent is the number of times I lose. So out of the 72 total attempts, 8 were wins, subtract 72 minus 8, whatever is left, that's the number of times I'm going to lose, right? Type that whole thing into the calculator. I will recommend the following. Don't break this up and do like the red part on your calculator and hit equals, and then the green part and hit equals, and then the blue part and hit equals, and then like try to multiply them together on your own, because the red thing is going to give a really, really big number. The green is going to give a really, really tiny decimal with a lot of decimal places, and you need to keep them all. So most people are not going to want to like type in all of those decimals again. So it's better if you just type the whole equation into your calculator all at once. It'll go off the edge of the screen. That's fine. Your calculator will keep track of it. Keep the whole thing there all at once. Second recommendation, use parentheses, exactly like I've drawn them on here, because otherwise, chances are you're going to type something into your calculator, and your calculator is going to try to apply order of operations in a way that you didn't intend, and it's going to attach things together that you didn't want to have attached together. So parentheses around the red part, parentheses around the base of the green part, parentheses around the base of the blue part. 72. And then the NCR lives in the math menu. So I'm going to hit math. I'm going to scroll over here to probability, and I'm going to go down to NCR. Enter, blam, there it is on the screen. 8. I'm going to close those parentheses and open a new set of parentheses. 1 divided by 6. Close those parentheses. You don't need to do anything special for fractions. Just hit the divide button. Keep the fraction inside parentheses. So you got the 1/6. Raise that to the power of 8. Hit the cursor. Get out of the exponent. New set of parentheses. 5 to the power of 6. So that's my losing probability. Close those parentheses. Raise that to the power of 64. So it doesn't fit all in one screen. That's fine. It's all there. At this point, before I hit enter, I can cursor left and right. So if I wanted to see the first part of the equation, cursor moves slowly, but I can go over there and see that. All right. So on the screen previously, I did just the equation as I have it typed right now. And I got, you can see at the very top there, 0.060988, blah, 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 blah. Okay. So that's the decimal version. And then on the next line, the middle one on the screen right there, I put the times 100 right on that same line of calculation. And so that's how I got the 6.0988. So that is actually in percent form. All right, we'll go ahead and try this next one on your own. What's the probability of rolling 72 dice and getting exactly 9 6s? Hit pause, write down your equation, see if you can get it in your calculator to get the correct answer. And once you have done that, hit play again. I'll rejoin you. So we should get this equation. Pretty much the only thing that changes is the 8. In what I wrote, the 8 is going to change to a 9. So this 8 changes to a 9. This green 8 changes to a 9. And then in blue, instead of 63 losses, this time I'm only, sorry, instead of 64 losses, this time I get 63 losses or failures, whatever you want to call it. And that should give us either in decimal form 0.0867 or as a percent 8.67%. Okay, one last example. What's the probability of taking a 20-question multiple choice test with 5 options? And you completely have to guess because there are actually not any questions written. What's the probability of doing that and getting exactly 4 questions right? Okay, well, probability of K, the number of successes being 4. Let's take a look. So the red part, so there's 20 questions and I'm looking to get 4 of them right. It doesn't matter which 4. It could be questions 1, 2, 3, 4. It could be questions, 16, 17, 18. It could be whatever 4 I want. So just how many different combinations are possible where I get 4 of the questions right. Times, and then in green, okay, so each of the multiple choice questions has 5 options. Only one is the right answer and 4 of them are not. So we could write it in fraction form, you could write it in decimal form, it doesn't make any difference. But 1 out of the 5 options is correct. And my exponent is going to be 4 because I'm asked about getting 4 correct. Okay, so in green, the base, just to repeat, the base, that's the probability of getting 1 trial correct. So it's a multiple choice question with 5 options. 1 out of 5 is correct. Okay, in blue, this is all about failure. So the base, the probability of getting it wrong. Multiple choice question has 5 options. 4 of them are the wrong answer. So 4/5 is my chance for each question. That's my odds of getting it wrong. And the exponent on the blue part is going to be the number of questions I would get wrong. So if there's 20 questions total, I'm asked about getting 4 correct. That leaves 16 of them not correct. Right, and then if you wanted this as a percent, we could put times 100 at the end. If you don't want it as a percent, then don't put times 100 and you'll get the decimal version. So we're going to start the parentheses, 20, math, probability, NCR, 20 NCR 4, close the parentheses, new parentheses, 1/5, close those parentheses, raise that to the power of 4, cursor over out of that exponent, new parentheses, 4/5, that's the probability of getting it wrong. Got too many 5s in there. All right, and close the parentheses, raise that one to the power of 16. Okay, so if you want to put times 100, that'll give you the percent. If you want to not put the times 100, it'll give you the decimal. I'm just going to leave it as the decimal. So I should get 0.218199, blah, 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 okay, whatever. And if I change my mind and decide that actually I do want to get the percent, I just hit times 100 now. So 21%, 21.8% is the probability that I would get exactly 4 questions correct purely by guessing.